Lesson: Evaluating and fine-tuning forecasting models for optimal supply chain performance. Evaluating and fine-tuning forecasting models are crucial components for optimizing supply chain performance and facilitating effective demand forecasting. These models form the backbone of predictive analytics in supply chains, enabling businesses to anticipate demand fluctuations and allocate resources efficiently. A robust forecasting system not only streamlines operations, but also reduces costs, enhances customer satisfaction, and improves overall business resilience. The practical application of these concepts requires a detailed understanding of tools, techniques, and frameworks that can be directly implemented to address real-world challenges. The first step in evaluating forecasting models involves selecting appropriate evaluation metrics that reflect the model's performance in real-world scenarios. Commonly used metrics include mean absolute error, mean squared error, and mean absolute percentage error. Each metric has its advantages and is selected based on the specific context of the supply chain. For instance, MAPE is particularly useful when dealing with data that spans multiple magnitudes, as it provides a percentage error that is intuitive to interpret. Conversely, MAE and MSE are more suitable for datasets where the cost of error needs to be minimized in absolute terms. Once the forecasting model is evaluated, fine-tuning becomes essential to enhance its accuracy and reliability. This process involves adjusting model parameters and incorporating additional data inputs to better capture the underlying patterns and trends. Techniques such as cross-validation are employed to assess how the results of a statistical analysis will generalize to an independent dataset. Cross-validation provides insights into the model's ability to handle unseen data, thereby preventing overfitting. In practice, the fine-tuning of forecasting models is often supported by software tools and frameworks that facilitate data manipulation and model optimization. Python's scikit-learn library, for example, offers a suite of tools for model selection and evaluation through hyperparameter tuning, which involves systematically adjusting the parameters of the forecasting model to identify the optimal configuration. Such tools allow professionals to automate the tuning process, saving time and increasing efficiency. A practical application of these concepts can be observed in the case study of a leading retail company that successfully optimized its supply chain operations through advanced forecasting models. By implementing a combination of seasonal decomposition of time series and machine learning algorithms, the company was able to achieve a 20% reduction in stockouts and a 15% increase in inventory turnover. This example underscores the importance of selecting and fine-tuning appropriate models that cater to the unique characteristics of a business's supply chain. To further enhance forecasting accuracy, integrating external data sources such as economic indicators, weather forecasts, and social media trends can provide additional context that improves demand predictions. For example, incorporating weather data has proven to be particularly beneficial for businesses in the retail and agricultural sectors, where demand is highly sensitive to climatic conditions. By using advanced data analytics platforms, organizations can seamlessly integrate these external variables into their forecasting models, thereby enhancing their predictive capabilities. The deployment of ensemble methods, which combine multiple forecasting models to produce more accurate results than any single model, is another effective strategy for fine-tuning forecasting models. Techniques such as bagging, boosting, and stacking allow for the aggregation of different models' predictions, mitigating the weaknesses of individual models and leveraging their strengths. This approach is particularly useful in complex supply chain environments where demand patterns are influenced by a multitude of factors. Despite the advancements in forecasting techniques, it is important to recognize that models are only as good as the data they are built upon. Therefore, maintaining high-quality data is paramount for accurate forecasting. This involves regular data cleaning, validation, and updating processes to ensure that the data reflects current market conditions. For instance, a study on supply chain analytics highlighted that companies that regularly updated their data sources realized improvements in forecast accuracy by up to 25%. In conclusion, Evaluating and fine-tuning forecasting models are integral to optimizing supply chain performance. By leveraging appropriate evaluation metrics, utilizing tools and frameworks for model tuning, and integrating external data sources, businesses can significantly enhance their forecasting accuracy. The implementation of these strategies not only improves operational efficiency, but also provides a competitive edge in the market. Through continuous evaluation and refinement, forecasting models can adapt to changing market conditions, ensuring sustained supply chain resilience and efficiency.